Hello, sorry that I'm not able to be there today with you guys in class. Hopefully you guys are able to follow along in the notes and understand all this stuff about concavity. But if you guys have any questions, please either text them to me on Remind or email me on School Loop, or if you want to hold on to them until Monday, that works as well. So for concavity, let's go ahead and get started. Let's first look at this Desmos, and you guys can kind of see what's happening, and then we'll fill in some of the blanks on your worksheet. It says to slowly drag the slider from 0 to 2 from left to right. So as we drag the slider, I want you guys to see what's happening to this line. Now I want you guys to notice what's happening to the slope of that tangent line. Now I already know that the slopes are positive because this is an increasing function. So as we look at the slopes, yes, of course, they're going to be positive. But what's happening to the slopes as we get further and further to the right-hand side? You may notice that the slopes are getting steeper and steeper. So they start off pretty horizontal at 0, and then they get steeper and steeper and steeper as you go along the curve. I want you guys to also notice the tangent lines. So notice how these tangent lines are in a specific location in relationship to the curve. So notice that they are all below the curve on this side of the graph. And that is a property of the curve when it is this shape, which we're going to talk about the what you call this shape in just a minute. But this is a tangent line that lies below the curve. It'll change when we go on the other side of the graph when the shape changes. But right here, where it curves up like that and the slopes are getting steeper, the tangent lines are always going to be below the curve. So this is what we're going to write down and fill in our notes in just a second. So let's talk about it. We call it concave up. I have a little phrase I like to say, concave up like a cup. So if you notice, it's not a full cup, but you can obviously see it's only half of one here. So this is an increasing function that is, oh, you can't see it. This is an increasing function that has a positive slope. So notice that it's increasing and the slopes are, and it's concave up, excuse me. So the slopes are getting steeper and steeper and steeper. This is also concave up, but it's decreasing. So notice that the slopes are still getting steeper and steeper and steeper, and that might be kind of counterintuitive to you because it's going down. But this slope over here at this furthest point to the left is very, very steep in the negative direction. So the fact that it's getting less steep but in the negative direction means that these are getting less and less negative. Well, if a number is getting less and less negative, it's actually getting bigger. So it is getting less steep, but it's getting bigger and bigger and bigger. So keep that in mind, that these are concave up as well. Notice the tangent lines are all below the curve. So let's go ahead and fill that in on your notes. Sorry, give me a minute to get the pen that I want to write with. All right, let's see if this works. So concavity deals with the shape of the graph. Fill in shape. And again, the first one we talked about was concave up like a cup. The slopes are either going to be increasing at an increasing rate, or, and so that's like the first picture. I'll actually draw it down here because I want you guys to as well. So if it's concave up with an increasing function, it's going to look like this. So that would be increasing at an increasing rate. Notice that if I draw a bunch of tangent lines, I'll draw them in red. If I draw a bunch of tangent lines, this one's not very steep, and then they get steeper as I go. So notice that that's called increasing at an increasing rate. The alternative is that they could be decreasing at a decreasing rate, or decreasing at a decreasing rate. And for a picture of that, that might look like this. So the function's still concave up with the shape, but it's going down now. And if it's going down and I draw a bunch of tangent lines, notice how steep this one is, but in the negative direction, then it gets less steep, still in the negative direction, and then even less steep, but still negative. So those slopes are decreasing, but at a decreasing rate. They're getting less steep, but they're going down. All right, in other words, slopes are getting more positive or less negative. So for this first example, these slopes are getting more positive, and for this example, these are getting less negative. Tangent lines lie below. Tangent lines lie below the curve. This is going to be especially helpful when we start talking about approximations and whether or not we're looking at over approximations or under approximations. So just keep that in your repertoire for right now, that the tangent lines are going to be below the curve when it's concave up. All right, let's go back to our Desmos really quick and look for what happens when it's concave down. So same graph as before, but now we're looking over here on the negative side of the graph from -2 to 0. Notice that this shape is different. So it's not concave up like a cup anymore. We call this one concave down like a frown, or at least I do. So if you look at this slider and you kind of slide it along, notice that this function is increasing. It's going up. And the slope right here over here at -2 is pretty steep. But as I get closer, like over here at -1, it's much less steep. And then as I get closer to 0, it's getting more and more horizontal. So these slopes are positive, but they are positive at a decreasing rate. So they're still increasing, but they're increasing at a decreasing rate because they're getting less and less steep as you move forward. So that's one of the properties of a concave down graph, is that if you look at the slopes along that curve, that they're going to be getting less and less steep as you go through. The tangent lines, notice that the tangent lines all lie above the curve when it's concave down, so all these tangent lines are actually on top of the curve. So that's another property for concave down. And then we're going to write this down in our notes as well. So again, notice these lines. So it's concave down, but it's increasing. The tangent lines are all above, and they're getting less and less steep. We go from a pretty steep tangent line to less and less steep until it's pretty close to 0. Alternatively, if it's a decreasing function, if the function is going down, the tangent lines are still above the curve, but notice that they're getting steeper, but they're getting steeper in the negative direction. So since they're getting steeper in the negative direction, they're getting more and more negative slopes, which means that the slopes are getting smaller and smaller. So for that second part, we have concave down like a frown. The slopes are either increasing at a decreasing rate. They're either increasing at a decreasing rate. So here's an example of that. If it's increasing but concave down, it might look like that. If I draw the tangent lines, here's a slope that's pretty steep. And then if I draw another one, it's getting less steep. And then here's another one, it's getting less steep. Notice that all the tangent lines are above the curve, but the slopes are increasing. They're going up. The function is going up, but at a decreasing rate. So they're positive slopes, but getting less and less positive as you go. The alternative to that is that the slopes might be decreasing at an increasing rate. And again, a picture of that. So a function that's decreasing concave down might look like this. And if I draw the tangent lines, here's a tangent line that's pretty close to 0 but negative, and then it's getting a little steeper in the negative direction and even more steep in the negative direction. So notice that those are getting steeper and steeper, or in other words, more and more negative as you go. So in other words, slopes are getting less positive, like the first example, or more negative, like the second example. Tangent lines lie above the curve. All right, let's look at that example down below, number 2. For this one, I actually do want you guys to graph the functions. If I was there, I would have had you guys graph them on your own, but since I'm not there, I'll graph them with you just to make sure that they're all perfect and correct. So it says to graph the function x cubed in red on the graph to the right. Hopefully you guys have different colors. Hopefully you have a red, a blue, and a green, but if not, maybe you can just get out whatever colors you have. And then cross off the words in the directions and change them to whatever colors you have. So I happen to have red. Let me change it to red. All right, so they want me to graph x cubed in red. So here's a graph of x cubed. It goes through 0, 0, 1, 1, 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. Kind of goes off my graph up there. It also goes through -1, -1, and then -2, -8. So if I connect this function in the shape of a cubic graph, it might look like this. All right, perfect. Next part, that's the original function, that's f of x. So I'm going to go ahead and label that f of x. It wants me to graph f prime in blue. Well, the derivative of this function, f prime, I'll go ahead and actually calculate it here. F prime of x is equal to the derivative of x cubed. That's 3x squared. So this is a parabola that's centered at the origin, so it goes through 0, 0. It's stretched by a factor of 3. So instead of going over 1, up 1, it's going to go over 1, up 3. 1, 2, 3. So this function looks something like this. And that's f prime of x. And last but not least, in green, they want me to graph the second derivative. So f double prime of x. And the derivative of 3x squared is 6x. So that's a linear function that's centered at the origin, 0, 0, and it goes up 6 over 1. 1, 2, 3, 4, 5, 6 over 1. Down 6 over 1. Connect this with a straight line. Best I possibly can. Let's see if we can do it. Oops. That is not what I thought it was going to be. Let's try that again. Sorry. I'm not on my normal iPad, so my lines are not as... There we go. Good enough. F double prime of x. Okay, perfect. So we have a graph of f of x, the original one in red. We have a graph of the blue one for f prime of x, and the green one for f double prime of x. So, number 1, or part A, I guess you could say, it says, let's look at the interval from 0 to 2. So we are looking over here on this side of the graph between 0 and 2. And they're asking us information about f prime, and f double prime. So let's look at f first. They want to know if f is concave up or concave down. So notice this red graph right here is concave up, like a cup. So it's curved up like this function is. So therefore I want you guys to circle concave up. I'll just highlight it. The second part, f prime is increasing or decreasing. So notice f prime, this blue function right here. Notice that when the red function between 0 and 2 is concave up, the blue function, the first derivative, is going to be increasing. The reason that this function is increasing is because we said the slopes were increasing at an increasing rate. So since they are increasing at an increasing rate, this function is going to be going up. So increasing. And f double prime, if we look at f double prime, the green function, notice that f double prime is positive. It's above the x-axis. So because it's positive, the second derivative is positive, then that's because the blue function was increasing. Since the blue function is increasing, therefore its derivative, which is the second derivative, will be positive. So these three things are connected. When the first original function is concave up, its derivative will be increasing and its second derivative will be positive. On the other half of the graph, from -2 to 0, that's over here. The original function is concave down. Notice that the shape of the graph is concave down like a frown. So let's highlight down. F prime is, if we look at the derivative in blue, the options are if it's increasing or decreasing. Well, notice that f prime is actually decreasing here between 0 and 2. The reason it's decreasing is because on the red function, these slopes are getting less and less steep as we go, which means its derivative is going to be getting less and less steep, or not steep, but less and less in its magnitude. So the values of the derivative will be going down to 0, since on this red graph, the values of these slopes are getting closer and closer to 0 as well. So if the original function is concave down, the first derivative will be decreasing. And last but not least, the second derivative will be, if we look at this green function over here, because f prime, the blue one, was decreasing, then the second derivative at this point would be negative, since its original function, which is the first derivative, is decreasing. So negative. I know it's a big mouthful to try and kind of relate all these things together, but we'll practice a lot with them over the next week or so to make sure you guys are more confident with it. All right, I want you guys to try and wrap your head around that. Pause the video for a little bit. If you guys were all watching it together, pause it for about 3 or 4 minutes. I want you guys to write a summary telling me what this means to you. Try to go back and really delve into this. Ask the people around you. See if you can digest this and put it into your own words, and write a summary about the relationship between a function and its first and second derivatives based on concavity. Then when that is done, when you guys have finished doing that, you can unpause the video and we'll continue. All right, hopefully you guys had a chance to go ahead and answer that question. For number 3 on the back, it says the graph to the right shows an image of, and then it gives this function for this cubic graph. And it says to label the first and second derivatives and then, or find the first and second derivatives and then label them on the graph. So the first derivative of this, if we find the derivative of 1/6 x cubed, we'd bring the 3 down front, that would be 3/6, which simplifies to 1/2. So this is going to be 1/2 x cubed. I'll make this a little thicker so you guys can read it a little better. That would be 1/2 x cubed, or excuse me, x squared. If I find the derivative of 1/2 x squared, if I bring down the 2, that would be 2 over 2, that's 1, so minus 1x to the first power, which is just minus x. And then negative 3/2 x, the derivative is negative 3/2, and then negative 1, the derivative is 0. So we have this parabola, this squared function. And then finding the derivative one more time to find the second derivative. The derivative of 1/2 x squared, bring down the 2, you get 2 over 2, which is 1x, so it's just x. The derivative of negative x would be negative 1, and the derivative of negative 3/2 is 0. So let's go ahead and label these on the graph now. The black one is the original function, that's our cubic function. So I'm going to go ahead and label the black one f of x. The green one is a parabola, that matches our first derivative, so I'm going to label this one f prime of x. And the blue one is the second derivative, it's a linear function, f double prime of x. Let's answer these questions. Number 4. It says, look at x equals 1 on the graph of f of x. So since we labeled these now, we know that the graph of f of x would be this black one. So let's go ahead and look at x equals 1 on this black function, which is right here. It says, notice that f of x is changing from concave blank to concave blank. So if we look at this side on the left, notice that it's concave down, like a frown, over here on the left-hand side of 1. But on the right-hand side of 1, it changes to concave up, like a cup. So let's fill that in. We're changing from concave down to concave up. It says the point where a function changes concavity is called a blank. And you guys do not know this vocab word yet, so let me tell you about it. It is called a point of inflection. A point of inflection. So anywhere that a function changes concavity is called a point of inflection. So x equals 1 is a point of inflection. Now, you're going to notice in the next couple questions that that has relevant information to the other two functions, the derivatives as well. So let's go ahead and figure out when a function has a point of inflection, what's happening on its derivative, so what's happening on the first derivative, and then what's happening on the second derivative. So for number 5, it says look at x equals 1 on the graph of f prime of x, which is the first derivative. So we're looking at the green one now. It says notice that f prime of x is changing from blank to blank. So here's that point on the green function. Notice that on the green function, the derivative, f prime, is changing from decreasing to increasing. Let's go ahead and fill those in. We're changing from decreasing to increasing. And I hope you see how that corresponds to the original function. It was concave down to the left of 1. And if it's concave down, remember the slopes are increasing at a decreasing rate or vice versa. Therefore, the slopes are decreasing. And then concave up, like a cup, the slopes were either decreasing at a decreasing rate or increasing at an increasing rate. Therefore, the slopes are getting more steep. So hopefully you see how those correspond to each other. On that derivative graph, on f prime, it says, therefore, we have a relative blank on the graph of f prime of x. And notice that this is a relative minimum. Now, I'm also going to generalize this because specifically on this graph, we have a minimum, but it could just be an extrema. In other cases, I might generalize it to say that it will be an extrema because in this example, our function is changing from concave down to concave up, which meant the derivative was changing from decreasing to increasing. But if we were working with a different example that changed from concave up to concave down, our first derivative would have been increasing and then decreasing, which would have been a maximum. So it will not always be a minimum. It just depends on which type of concavity it starts with and which type it's changing to. So keep that in mind, is that it will be an extrema. It will either be a relative minima or a relative maxima on the derivative. Let's look at 6. Number 6 says, now look at x equals 1 on the graph of f double prime of x. So that's this blue function right here. If we look at x equals 1 on this graph, it says, notice that f double prime of x is changing from blank to blank. We have negative values to the left and positive values to the right. So it's changing from negative to positive. Therefore, we have a 0. We have a 0 on the graph of f double prime of x. So these three things, it is very important for us to understand the relationship between these three things. If a function has a point of inflection, its derivative will have an extrema at that point, either a maximum or a minimum, and its second derivative will have a 0 at that point. Because the second derivative corresponds to negative values, since it's concave down on the left, the second derivative is negative on that side. Since it's concave up on the right-hand side, the second derivative is positive. And since it's changing, therefore, the second derivative would be 0 at that point. All right, I want you guys to pause the video again. This time take a little bit longer because I want you guys to make sure you include all of these vocabulary words as you guys write a summary of what we just talked about. So go back, pause the video, try to understand everything we talked about, and then, like I said, write a summary using the words concave up and down, point of inflection, whether or not it's increasing or decreasing at those points, if it has a minimum or a maximum, positive, negative, and 0. So, and then relate them to the derivatives. So the original function, the first derivative, the second derivative. And then that way you guys will have a nice summary of what it means to you so far. We can kind of tweak it when I come back just to make sure that it looks good. But for right now, pause the video and try to do your best to do that. All right, and the last thing I want to fill in today, we started filling in this chart the other day, and this chart is going to be so helpful for us as we start to answer questions about these problems. We said that the original function being positive 0 and negative actually has nothing to do with the derivatives because it's just a y value, and when we take the derivative of the y value, it's equal to 0 anyway. So these all are going to be left blank. We did fill in some of these. We said when the original function is increasing, its first derivative will be positive. So let's go ahead and fill that in one more time. We said when the first function was decreasing, its derivative would be negative. And if a function has a maximum or a minimum, its derivative will be equal to 0, or it might be equal to 0, or it might not exist. So DNE does not exist. And then we also drew in these arrows. So I want you guys to redraw these arrows in on this chart as well. If our function's derivative is changing from positive values to negative values, that indicates a relative maximum on the original function because the original function would have been changing from increasing to decreasing. And alternatively, if we're reading it the opposite way, if your derivatives are changing from negative to positive values, then the original function would be changing from decreasing to increasing, and that would be a relative minimum. So go ahead and fill those two things in on your chart just to make sure you have them for later. All right, and then last but not least, for concavity. Now again, if something is concave up, if a function is concave up, that means that the slopes are going to be either increasing at an increasing rate or decreasing at a decreasing rate, which means they're getting more steep. So if they're getting more steep, or more steep in the positive direction or less steep in the negative direction, but that just means that this function is going to be increasing. The slopes are going to be getting greater or going up. So if a function is concave up, its derivative is increasing. If a function is concave down, its derivative is decreasing. For the same reason that it's concave up, but the opposite. So in the sense that concave down means that the slopes are getting less steep. Now, a point of inflection, a possible point of inflection. Remember on the example we just finished, if there's a point of inflection on the original function, it's going to have either a max or a min. a max or a min on the first derivative graph. Notice that it says only it changes sign. If it doesn't change sign, it's not going to be a max or a min. It'll just be a flat part. Now, to fill in this last row in the table, I want you guys to see the similarities between this row and this row. Notice that these are the same things: increasing max or min, decreasing, increasing max or min, decreasing. So the way that the original function and its first derivative relate to each other is the same relationship that the first derivative and the second derivative actually have with each other. So we're going to fill in the same things right below here. If a function is increasing, its derivative will be positive. If a function is decreasing, its derivative will be negative. And if a function has a max or a min, its derivative will either equal 0 or not exist. So again, notice the relationship between these to this because of the way that the derivatives relate to each other. All right, that's all we're going to do for today. So go ahead and make sure you have all those written out, and then we will continue tomorrow or Monday.